So hello and welcome everybody to the next in our series of Kickstarter Colloquium. Just to begin with our usual range of reminders, the colloquium will be recorded for the benefit of those who can't join us in person. And if you prefer not to appear on that recording, please keep your camera off. And if I could ask you to kindly keep your microphone muted unless you're actually speaking so that we don't have interference, that would be great. You are welcome to post questions at any time for the speakers using the Zoom chat screen, and we'll either address those as they come up or we will have a Q&A at the end of the session. So for this colloquium, I'm delighted to introduce Steph Merritt and Grigori Fedorets, both from Queen's University in Belfast, UK. And they're going to describe for us a hugely ambitious project, a survey simulator for all of solar system science that LSST will do. So very much looking forward to hearing your talk. Steph and Grigori, take it away.
Thank you. Thank you, Rachel. I think I will begin. Okay, great. Sorry about the delay. Thank you everybody for coming. I'm Grigori Fedorets, and together with Steph Merritt, I'll be talking about the survey simulator for solar system science with LSST. It's a joint effort between people from Queens, and as you can see on the bottom, there have been quite a lot of other people also involved in this work. So I would like to acknowledge all of the work that has been done. Yes, so the outline of this talk is I will first briefly talk about why would one like to study small solar system objects, as they are clues of ancient crimes haven't done by planets. Then what are all the different astronomical surveys have been doing for solar system objects, and why, and the different observational biases which occur when you attempt to study these objects in great numbers, and what can be achieved when we get rid of them. And finally, the work been doing the survey simulator will be presented later. So I've seen that many people in the audience are already with solar system background, but in case you are not, just a brief reminder of how the solar system looks like when you take a look at the semi-major axis versus eccentricity and inclination. So here on the starting from the left, you can see the populations of near Earth objects, which is here between 1 and 2 AU, and then there is the main belt population and the Jupiter Trojan population. There are much more. This is just because when you plot all of these objects, you can on top of them each other, there are much more. And then when you skip from 5.2 AU all the way to the orbit of Neptune, there are some objects in the middle, not too many, but then the new belt starts beyond the orbit of Neptune, which is then called the Kuiper belt or the trans-Neptunian region. So it's, as you may see from this distribution, it's the shape of these the shape of the population is it's not intuitive why it is like that. So there needs to be some explanation of why they look like this. So there are some contemporary mechanisms which explain things. For example, these Kirkwood gaps here in the main asteroid belts are due to the orbital resonances with mainly Jupiter, also Saturn, and the population of near-Earth asteroids is also can be explained due to contemporary dynamical processes. However, there are some things that cannot be explained by contemporary processes. There is something which happened in the past of the solar system, for example. So, for example, this scattered region of the trans-Neptunian population is it's not cannot be explained by some contemporary processes. Moreover, if we take a look again at the main belt, but in terms of their masses. So here you can see this is what the masses of the different components of the main asteroid belt look like, and the main takeaway from here is that in the inner belt there are more of these red objects, and the outer belt, the more of these, you may say, blue objects or C types, which are carbonaceous, and then the S type, the red ones, are like the silicates. Just again, this is this discrepancy can it is not really something had to happen in order to make these the main asteroid belt look like this. So what happened? What happened to in order to for the small solar system object distribution to become as it is known today? So that is again the crime, the clues which are left from the early stages of the solar system. So coming from so around 4.5 billion years ago, after the solar system formed, there were some dynamical processes between the giant planets. So there is something called, there's the Grand Tex scenario, which means that Jupiter and Saturn first migrated inwards, and then they turned back, and then they formed the scattered S types, and then the asteroid belt makes up, producing the planets of the comparable size. So these are simulation results. Then there is then there's another thing called the Nice model, which tells us this is just a sketch of what is expected to have happened there. So that means then Jupiter and Saturn were locked in a mean motion resonance with each other, which excited their orbits and essentially threw away the majority of small solar system bodies, and the ones that remained would follow that formed the Trojans and and everything else. And then when the Nice model was subsequently updated, it showed up that in order to produce the current architecture, you would require a fifth-size giant that would make it easier, and then the close encounter with Jupiter and Saturn would, due to interaction with said fifth planet, would lead to a quick separation, again leading to a better understanding of the better commensurability with the current population. And then the subsequent refinements gave better understanding of distribution of Trojans and irregular satellites of giant planets. So, however, the timing of these different scenarios, and then there was different scenarios, it's still not clear what had happened and in what order. So did the Grand Tex happen first and then happened this Nice model of instability, or was there an early instability which caused all that? So the timing constraints will come from future observations, there has been, and the observations come mostly from astronomical surveys. Here's just an example of all the different types of surveys that have been conducted for solar system. This is of course not exclusive. Many different surveys exist, but here's just an example of some significant results for them. So here is the plot from the Sloan Digital Sky Survey, which is a photometric survey showing the different colors of different asteroid families. in the main asteroid belt. Then recently, earlier this year, the Gaia survey published a sample of 60,000 spectra, which again characterize spectra are. This was the largest spectral sample of mainly main belt asteroids so far. Then in the outer solar system, the OSSA survey discovered many trans-Neptunian objects all the way. It was a dominated survey discovering the trans-Neptunian objects and in different direction, and since it was a well-characterized survey, and many predictions can be made of the actual population of the outer solar system. And coming closer to home, in the many surveys are then dedicated to discovering near-Earth asteroids because they are obviously causing the threat to Earth. So the number of object discovered mainly from the Catalina Sky survey and the Pan-STARRS survey are the two main surveys that have been discovering near-Earth objects, and also as collateral, you may like also discovering, for example, main belt asteroids. But we're here for LSST, which is the next and exciting survey, which will discover much more. So currently, for example, just to give you an idea, around 1 million, over 1 million of all small solar system bodies is known, but it is expected that solely in the main belt, over 6 million, around 6 million will be discovered, and it will also contribute to discovering many more of throughout the entire solar system. So before getting too excited about the upcoming LSST discoveries, there is a word of caution. So there are what you need to know what you are discovering. It's when what you are discovering is not the entire truth, as you can see here on the image on the right hand side. By the way, this resembles the NEA distribution of major axis versus eccentricity for those who do inner solar system. So yeah, just to give you an idea of different types of observational biases which are present in all surveys. In some surveys, in some surveys, some biases are more prominent than the others. But just to give you an idea what these biases may be, for example, the flux biases, when the brighter objects are detected more often, but we don't always know what is the reason for that the object is more brighter. It may be further away. It may be further away at the moment. It may be darker. It may be observed in a filter where it is darker compared to the other one. Then, for example, there's a pointing bias, which is targeting specific areas in the sky where many objects are detected, but they don't give a picture. For example, the NEO surveys often point towards the ecliptic and not discover many objects off ecliptic. Then the ephemeris bias is so following up newly discovered bodies, constraining the orbits, then would require some assumptions which may not be correct for all bodies. So the ones for which the assumptions are false will not then be followed up, and will not, the orbits won't be correct, and these kind of objects will be under represented in the population. And then the detection biases, so the cadence of the survey can be optimized for a certain sky velocity. So the objects that are too fast or too slow can become left out. And the other problem is that, so this, like I said, this is just an example of some biases that are present, and also they are often entangled within each other. So in order to account for these observational biases, many procedures exist to debias them, and and while these debias procedures are done, they also open some avenues for new exciting science. And I would just like to give you two examples. The first one comes from the inner solar system. Here is on the left hand, starting from the left hand side, you can see the orbital distribution of a near Earth object as a function. If the video is playing, I think it is on a loop. It should. No, let's go back. So this is the 7 major axis versus eccentricity inclination, and this is what is the population of the asteroids as a function of the H magnitude, which is a proxy for the brightness and size. So this is a debiased picture of after tracking the re-observation of the Catalina Sky Survey. However, this is not the entire. There was a problem with that, because when they tried to see what was happening there, they saw that many objects were disappearing at low perihelion distances. So there was 10 times more objects that were predicted than they were observed, which resulted in a realization that the asteroids which come close to the sun, they do not drop on the sun, but they come close to the sun. They disrupt before falling into the sun. And when that was taken into account, this realistic population could be conceived. The other thing that is worth mentioning at this point is that these populations of different the size distributions of these populations are not complete. They are, because the fainter objects are less represented. As for example, you can see here, this is a paper from a couple of years ago, and it's probably different. So, but you can see that this is these lines over here represent the what is expected, and then the red one is what is discovered. So we don't know the entire truth of what's happening. For example, are there more darker objects here, for example? So the more you observe, the better idea you get. And this is not only true for NEAs, but this is true for all different solar system object populations. So when LSST comes, it will improve these of an order of several magnitudes. And another example is the current debate about the existence of planet 9 in the outer solar system. So on the left hand side, you can see a projection of several orbits. These are the distant orbits, the most distant small objects that are discovered in the solar system. So you can see that there's this black line, and then there are these orbits that it more or less follows the clustering of the orientation of these orbits is more or less following along this black line, which gives an indication that there is a massive body which is herding these objects and indicating that there might be a knife planet on the outskirts of the solar system. But here on the right hand side, there is a different plot which perhaps cautions about getting into conclusions. So here you can see these different points here, blue, red, and gray, are the discovery of the alignment of this perihelion. So which is exactly this, if it is along the line. So as you can see, yes, it is. They do indeed seem to there are not many over here. However, if you take into account the effect of observational biases, you can see which are represented by the dark squares on the background. So the darker ones represent the places on the sky where the opportunities to discoveries have been more prominent than compared to the more lighter ones. So these are the two kinds of things which are important to take into account, these different solar system populations. So I hope that I have convinced you that debiasing different solar system population is very important. And with that, I give the floor to Steph, who will tell us what we have been actually doing.
Thanks, Grigori. Can you hear me okay, yeah?
Yes.
Coming through? Great. Okay, so as Grigori has explained, astronomical biases are...
Oh, sorry. Yeah.
Thanks. Are a really big issue for surveys, and this is going to be especially important for the LSST. I've included this table again just to really hammer the point home. The LSST is going to perform the most comprehensive survey of solar system objects to date, millions of discoveries expected, an absolutely unprecedented opportunity for population studies. But of course, any observations we make are going to be inherently biased. And that's where a survey simulator comes into play. A survey simulator is a pipeline built to replicate the effects of well-understood astronomical biases on a synthetic population of objects. So by running several model synthetic populations representing your theories for what is actually out there through a survey simulator, and then comparing the output to what we actually see in our observations, we can actually begin to understand what may be truly out there underneath all of these biases. This has already proven to be a really successful debiasing method on smaller surveys like OSOS, which was mentioned earlier, but we are going to be scaling that up, like way up. Next slide. Thank you. So our survey simulator, surveySimPP, it's entirely open source, built in Python using pandas, and it was created to be really generalizable and really modular. Each bias is modeled by a filter. All filters can be turned off and on via a config file or customized by the user. Adding new filters is also very easy. And the really big thing is that it is applicable to all solar system small body populations, from near-Earth objects to trans-Neptunian objects and everything in between. Another benefit is that the survey simulator actually works as a layer over a piece of code such as objects and field that does the computationally expensive task of actually integrating the orbits of your objects to find if they lie in your telescope pointings. That's quite a lot of computational heavy lifting. That only needs to be done once. Once you've done that, you can then run our survey simulator layer multiple times with different settings to see what you get out of it. Okay, next slide. So this is the basic structure, and it's divided into two sections. So in pink on the left, we have calculations made of magnitudes and uncertainties. And then on the right in yellow, the various filters which mimic the effects of the LSST's observational biases. And as I said, all of these filters can be turned off and on or parameterized by the user via a config file without you having to go into the code. Or if you're more confident with the code, you can always go in and have a look yourself, create your own filters, make adjustments. Next slide. Okay, so the inputs. You take the output of a code pipeline like objects and field to get you the object ephemeruses and the associated telescope pointings. Then you also include the database of telescope pointings, so from OpSim, for example, or the actual pointings once the LSST is up and running. Then you take the object orbital elements in Keplerian or cometary format, their physical parameters, so including the absolute magnitude, color offsets for the filters you're interested in, plus any phase coefficients. And then optionally, you can also include cometary activity details like K and AF rho. Next slide. The magnitude is then calculated for a user-selected phase model, so linear HG, HG1G2, HG12 or 12, and that'll take into account distance, phase angle, the filter that the observation was made in, and any cometary activity. The magnitude is then adjusted if the user selects for trailing losses. This is not important for your very slow-moving objects, but for close-in sources like near-Earth objects, we would expect to see trailed sources, so where much of the flux lies outside of the PSF fitting kernel, so we can adjust for that. Next slide. The 5 sigma limiting magnitude at each point is then adjusted for vignetting, so the darkening of the field of view at the edges caused by the optics. Next slide. The signal to noise is calculated then along with the photometric and astrometric uncertainties. And then we move on to the filters. So next slide again. Okay, so the first is a footprint filter. Simply, is this object actually on the camera footprint? Something like objects and fields will probably give you a rough idea, but our filter basically lets you choose a circle, or you can choose the exact LSST footprint, which includes the chip and the raft gaps. An experienced user can also create their own if they like. Next. Then there's a choice to either remove all detections below a user-defined signal-to-noise ratio, or all detections fainter than a user-defined magnitude limit. Next. Okay, then we have detection efficiency. Detection is probabilistic, especially for fainter objects, and it follows a fading function that decreases as magnitudes increase. So we use this analytical equation from this paper, which is dependent on the simulated seeing and the according limiting magnitude. And the width of that is defined by the user in the config file. Next. We also have a saturation limit filter to remove all detections brighter than a defined saturation limit. Again, that can be defined by the user. Next up. And then finally, there's a filter which mimics the effects of the solar system processing pipeline for linking solar system objects. So if you want to discover which objects in your sample will be successfully linked automatically and reported to the Minor Planet Center. All parameters on this are also customizable by the user. So you can set the minimum number of observations in a tracklet, minimum number of tracklets in a track, so on and so forth. Next slide. Okay, the code then outputs all observations in which your object has been detected. So it will output the object ID, the object location, the field location and ID, the filter of the observation, the apparent magnitude in that filter, associated uncertainties, and the 5 sigma limiting magnitude at the object position and at the field center. Okay, next slide. So the survey simulator is currently in final validation and checks. Everything seems to be working. We're just kind of ironing out the last few creases, I guess. It should not be used for science cases just yet, but we are very close. We expect to be there before the end of the year. The QR code will take you to the repo if you do want to give it a whirl. Just please bear in mind, we are still working on it. It is in active development. There's extensive documentation out there as well. Grigori is currently working on the paper. And in the future, we hope to add support for shapes and rotation of objects, explicit support for Rubin Sim to generate the object positions in field, explicit support for other surveys. So we could maybe extend this even beyond the LSST. It is very easily customizable to do that, and a lot more. So if anyone has any suggestions for filters they'd like to see or things they'd like to see implemented, let us know and we can see about putting it in version 2.0. I think that's it. Thanks very much, everyone, for listening to us.
And thank you very much, Steph and Grigori, for such a wonderful talk. This is a tremendous piece of work you've put together. There's an awful lot of work that's gone into this. So please, everyone, feel free to put your questions in the meeting chat screen. And to get the ball rolling, I'm going to jump in with one of my own. And I know the recent launch of the near-Earth satellite constellations has been a big concern to the Solar System Science Collaboration. And I know that there has been talk of even moving forward some of the main surveys for solar system science to make sure that they get done in case we lose the night sky. Can you speak a little bit about what impact that has on estimating survey biases?
Thank you for the question. I guess I can begin without answering. I mean, so what I've heard, the number that I've heard is that around 10% of all images are going to be affected. So, and then if also the background limit of the night sky will be, in that sense, rising up. So the limiting magnitude will be will be higher than expected. So that's, however, for the so that, yes, there will be an effect. The other effect that will happen is that the majority of these, to my understanding, the majority of these trailed objects will be during the twilight time, which would be quite beneficial to also use for some more weird objects, for example, the ones that are inner to the orbit of Earth. So that would be that these would be affected. However, but for the majority of objects, like it won't be we will not be able to confuse these objects with real real asteroids, because they have characteristically very fast objects, and I think they're so fast that they go through the entire field of view during a single exposure of LSST. However, I'm not familiar if there are any mitigation in place from the LSST, unfortunately.
I think.
Sorry, go ahead, Steph, please.
I was just going to say, I think that it's something we could look into modeling in the future for the survey simulator, either statistically or more explicitly, because it's an interesting problem, and it is something that may affect some observations, and that might be something that people are interested in. So whether it could be something that will be modeled statistically by just assuming 10% of observations are affected within a certain time range, or more explicitly, if we know the positions of the satellites themselves, it would be an interesting problem for future versions, I think.
Yeah, I agree that you're unlikely to link an orbit between a NEOSat and an actual near-Earth object, but I was assuming that they would saturate enough of the detector, which, as far as I know, can't be effectively modeled and thoroughly removed, that you might end up losing one out of a triplet or a pair of observations, for example, meaning that you wouldn't be able to link the measurement properly. So presumably then that is going to impact your rate of recovery.
Yeah, that would, honestly, without any kind of mitigation effects, that would just count as a dropped observation, and that could be something that could be accounted for very easily. Yeah,
that's probably will affect more the NEOs, because the closer ones, because the outer ones, they move so slowly that
sure.
Probably
Sure.
Yeah, but we'll need to keep on thinking about this. Yes.
Yeah, we're not going to be adding any new features at the moment, but we are collecting ideas for the future. So that's definitely definitely a really good thing to bring up.
Something to bear in mind, sure.
Yeah.
So I have lots of other questions, but if anyone else has a question, please feel free to jump in and post it in the chat screen. But in the meantime, I was wondering about, you made an interesting point about the number of surveys that are out there, all with their different survey biases. And I'm wondering what the potential is for combining different survey data, particularly in complementary wavelengths, like infrared, for example. Obviously, that's going to complicate your survey efficiency estimation quite considerably, but conceivably in the future, that might be an interesting thing to do, no?
It sounds like a very complicated thing to do, but it also definitely sounds like a really interesting thing to do. It's quite an ambitious project now, but people do like to mention things to me, and then I think, yeah, I'd like to do that as well. Yeah, that's a really interesting, really interesting sort of point to bring up, especially when you're looking at things like Planet 9 and these supposed extreme TNO orbit alignments, and originally that data was coming from several different surveys. So being able to deal with that in a more comprehensive manner would be very interesting.
But as you say, a large increase on an already tremendous project. This is a hugely ambitious work.
Yeah, but I think it would be a worthwhile one. Yeah.
Not to give you several decades more work to do, but you know.
But just to talk, you were talking about the overlap. If I could just mention that ESA's Euclid mission will
Mm.
be launching also in a couple of years, and it's a near infrared mission, which, well, it avoids the ecliptic and it avoids the Milky Way, but there is in the southern hemisphere there's quite a there is an overlap where a lot of can be kind of combined from that region. Obviously that's restricted to some point, but that's the first one, and it's also going to its limiting magnitude is on the same order as LSST. So that's the first one that comes into mind when thinking about with which survey we could combine the data.
Right, and there's also the Roman space mission from NASA, which will do a high latitude survey, I believe.
Okay.
So that will launch slightly later, I think, is the current plan.
Right.
Something to look into.
Yeah, another complementary data set to add to your workload.
That's what we do.
Well, this is a tremendous project, so congratulations to both of you, and I do look forward to seeing the paper. I think, are there one last chance for anyone to post your questions? Oh, good one from Angelka. Would you like to comment out loud?
Yeah, so thank you for the question. Well, LSST is expected to discover up to maybe a dozen of interstellar objects during its time, but so we do expect to find interstellar object with LSST, but this is also a tool to predict if you know the real distribution, if you have a distribution of interstellar objects, what direction they're coming from, what's their orbital parameters. So you can use this tool to assess at what distance, at what brightness you would be able to find it. For example, and you could also, like Steph mentioned, you can assume, well, we know two interstellar objects. One was a comet, like it had bodies of was a comet, and then Oumuamua was not a comet. It was an asteroid. It didn't have any seeable activity. So you could also assess, yes, there is an interstellar object coming. At what distance we would detect if it has activity, at what distance we could detect it if it doesn't have activity. What would be the difference, and then you could accordingly plan your follow-up observations and that kind of things.
Yeah.
And you said that we can expect maybe a dozen or so over the lifetime of LSST?
Yeah, well, something between, well, it's
I won't hold you to hard numbers.
and,
don't panic.
yes. It's a small number of statistics, yes.
Yeah. Very good. Good question from Henry Shea. Henry, would you like to repeat your question for the benefit of people watching in a recording of this?
Sure. I was trying to think of how to phrase this, so that's why it took me a while to post it. So, but I just want to maybe just ask a general question of how you, if you can talk more about how you handle comets. So I know Steph mentioned being able to adjust like the brightness functions of comets. I was wondering if you consider things like the fact that comets might have larger uncertainties because of astrometry of extended objects is, more uncertain. So whether, you take that into account, because, you might not detect, a comet because just the astrometry is off. I was just wondering if you could talk about that.
Sure. So as far as I know, currently we're only accounting for increased uncertainties in the case of trailed sources. I don't know if that applies to cometary activity specifically. I would probably need to double check the code. But handling cometary type objects more specifically is something that is also on our to-do list. So I will look into that, because it's a really good point you've made. And I would like to know if that's something we could easily put into the code if it's not already there. I would need to double check, but that's a really, really good question.
Okay, great. Yeah, thanks. I know it's definitely challenging, so no worries for sure. Thanks.
Thank you, Henry. Okay, well, if there are no further questions, let me thank Grigori and Steph again for a really interesting talk and a really tremendous project. Congratulations again.
Thank you. Thank you so much.
And thank you
Thank
all
you.
for coming.
Yeah, thank you so much for coming and listening to us.
It's been a great pleasure. And I hope to see you all at the next Kickstarter Telecon, which will be in about a week's time from now. So I'll see you all then. Bye-bye.